Alright students, in this video we're going to talk about loose star structures. We'll learn how to draw loose star structures for the covalent compounds. To begin with, I want to take a few examples of drawing the loose star structures for just the elements, and then we'll move on to the covalent compounds. Basically, the loose star structures are the representation of the valence electrons because remember, the valence electrons are the one that involves in the chemical bonding, not the core electrons. So it only represents the valence electrons. If I take an example of sodium, sodium has one valence electron. So if you have a hard time finding the valence electrons, recall that the group number actually tells you the number of valence electrons. Since sodium is in group 1A, it's got one valence electron. So I can go ahead and write down one dot, draw one dot on the top of sodium, and that represents the loose star structure for sodium. Now this dot doesn't necessarily have to be on the top. I could have this dot on the left side or even on the right or in the bottom. It doesn't really matter. Now let's suppose if I have magnesium. Magnesium has two valence electrons because it's in group 2A. So when I'm drawing those two electrons, I have to make sure they are as far away from one another. So I can put one on the top and one on the bottom, or I can put one on the right and one on the left. It doesn't matter as long as they are as far away from one another. Now the problem comes in whenever you have more than four electrons because you have four directions, so you can put those four electrons in every direction as far away from one another. But what if you have more than four electrons? How would you take care of that problem? Let's take an example. If I have nitrogen, nitrogen is in group 5A, so that means it's got five valence electrons. So I can go ahead and draw four, one in each direction, and then come back, start pairing them up. And it doesn't matter which one really you pair up, you just do one at a time. So I can pair up the one on the top, or even I can pair up the one on the left, or even the one on the right, or on the one on the bottom. It doesn't matter. And if I want to do, let's say, oxygen, which has six valence electrons, so I would do 1, 2, 3, 4, and then when it comes back to putting 5 and 6, I can start pairing up maybe the one on the top and the one on the bottom. Alright, so that's how you're going to be drawing the loose star structures for the atoms. Well, drawing the loose star structures for the atoms is not that important. What's more important is be able to draw the loose star structures for the covalent compounds. Now remember, the covalent compounds are made by sharing electrons. That's the foundation of the covalent compound. So we have to show how the electrons are being shared between the atoms, and we also have to show any electrons that are not shared or that only belongs to one particular element in the covalent compounds. So there are actually some rules that you have to follow when you're drawing the loose star structures. So I'm going to go over those rules, and I'll probably take one example as we move along. So let's just talk about drawing the rules on drawing the loose star structure. And let me take a CCl4 as my example. This is called carbon tetrachloride. So like I said, we only focus on the valence electrons, all right? So we have to make sure we count the total number of valence electrons. So that's always going to be your first step. So the total number of valence electrons is just basically going to be the addition of all the valence electrons of all the atoms you have in that particular compound. Now in this case, we have carbon. Now carbon is in group 4A, so it's got four valence electrons, so it's going to be 4 plus I have 4 chlorines, and each chlorine is going to have 7 valence electrons, so 4 times 7, and that's going to give a total of 32 valence electrons. So when you draw the loose star structures, you want to make sure you use all 32 electrons, no less than 32, no more than 32. Now let me give you a couple of other examples. What if you have a charge on a given chemical? How would you take care of the number of valence electrons in that case? And let's say I have NH4 plus. This is called ammonium, If you have a cation, so remember what happens when you have a positive charge, they are electron deficient, so they're going to have one less charge. If this was in a 2 plus, then it would have 2 less electrons. So when I'm doing the valence electrons on NH4 1 plus, I would have 5 electrons on the nitrogen, plus I got 1 electron in each hydrogen, and then since there is a 1 plus charge on it, I would have to subtract the total valence electrons by 1. So that's going to come out to be a total of 8 valence electrons. Okay, well, what would happen if you have a negative charge? Well, the negative charge means it's an electron-rich molecule, so you have an extra electron in there. And let me take an example of maybe CO3, 2 minus, that's called carbonate. Now, in this particular case, I got carbon, so carbon is going to be 4 valence electrons, plus I have I got 3 oxygens, and let me erase that. I got 3 oxygens, and each oxygen is 6 valence electrons. And then now since you got 2 minus there, so that's an extra electron in there. Remember, whenever we have a negative charge, it means you got excessive electrons in there. So then you're going to have to add 2 electrons to the total. So it's going to be 18 plus 4, 22, plus 2. That's going to be a total of 24 electrons in this molecule. Okay, so that's how you take care of the total number of valence electrons. Make sure if you have a positive or negative, you do take care of those as well. Okay, well, let's move on to the next step. Once you do calculate your total number of valence electrons, the second thing you have to do is pick a central atom. Obviously, whenever you have more than 2 elements in the molecule, one of them gotta be the central atom. If there's only 2, then you don't have to worry about the central atom. So there are some tricks that you can always use, and those tricks mostly work almost all the time. The first trick is hydrogen is actually never a central atom. So if you see a hydrogen in an element, in a compound rather, it's not going to be the central atom. Let me take an example. If I have water, so in water I got 2 hydrogens and 1 oxygen. So in this particular case, your central atom would be the oxygen, because hydrogen is never going to be the central atom. Let me take another example. What if I have H2S? In this case, I got 2 hydrogens, 1 sulfur. So like I said, hydrogen is never a central atom. That means your sulfur would be the central atom. Okay, I can take maybe another example. CH4. Again, hydrogen is not going to be the central atom, so it's going to be the carbon. Okay, well, there are going to be times when you don't have the hydrogen in the molecule. Then how do you determine your central atom? The second trick that you can use for the most part is the carbon atom. If you see in a carbon atom, that's going to be mostly the central atom, almost more than 99% of the times, unless it says otherwise. Okay, if I can go back to my example actually. I got CCl4. So in this case, I do have a carbon, so that means carbon is going to be your central atom. Okay, I can maybe take another example. I can just go back to the CH4. Remember I said if you have a carbon, that's going to be the central atom, and hydrogen is never a central atom, so that's the central atom. Or I can take CO2, that's carbon dioxide, and that carbon would be your central atom. Or I can even talk about CBr4, so in that case, carbon would be your central atom again. Okay, well, now there are going to be times when you don't have the hydrogen and you don't have the carbon, but you still have an equivalent compound. Then how do you determine the central atom? The next trick that you can always use is the atom with the fewest subscripts, and that's usually the less electronegative element, all right, except in cases of CH4. If you have a hydrogen involved, then use your rule 1 or trick 1 there. But if this is rules mostly when you don't have the hydrogen and don't have the carbons in there. So if you see the atom with the fewest subscript, which means less electronegative, that's going to be your central atom. Let me take an example. What if you have IF7? Okay, so in IF7, iodine has a subscript of 1 and fluorine has a subscript of 7. So that means iodine is going to be your central atom, and iodine is indeed less electronegative than the fluorine. What about SF4? Okay, so in this case, fluorine has 4 subscripts and then 1 subscript for the sulfur. So sulfur is going to be your central atom in this case, or I can take maybe an example of PCl3. Okay, so in this case, there's 1 subscript for the phosphorus, 3 for the chlorine. So as a result, phosphorus would be your central atom. And if you look at the electronegativity, phosphorus is indeed less electronegative than the chlorine. So this is how you're going to be determining the central atom. Make sure you don't skip the steps. Make sure you count the valence electrons, pick your central atom, and then move along as you're going in there. Okay, so remember we have taken our example at CCl4, and that's what we're going to be looking as we moving along. So once you determine your central atom, the next step is to place your central atom. Okay, so I got carbon as my central atom, and place the surrounding atoms as far away from one another. So I got 4 chlorines. So the best way to put 4 chlorines as far away from one another by putting them in 4 directions like this. Okay, so that's the best way of doing it. So that's this rule 3 right there. So we're done with that. Okay. Once you have done so, the next thing you want to do is place 1 pair of electrons or a bond. Okay, so I'll talk about that in a minute. But 1 pair of electrons between the central atom and each of the surrounding atoms. So what I want to do here, I want to put 1 pair of electrons between the central atom and the surrounding atoms, just like this. Okay, now what that really means is this electron pair that's being put between the central atom and the surrounding atom belongs to both the central atom and the surrounding atom. That's because, remember, the covalent bonds are made by sharing the electrons. So those 2 electrons are being shared by both of them. So if I look at it right now, if I draw a circle, this carbon is going to have these 8 electrons already. Okay, and so far each of those chlorines have only 2 electrons because they are being shared by both carbon and chlorine. So that's how you look at it. Now, for the most part, you don't really draw the electrons between the atoms. You actually draw a bond. Okay, so drawing a bond or putting 2 electrons between the 2 atoms is the same thing. So from now on, what we're going to be doing, we actually going to be drawing that shared electrons between the atoms in the form of the bond. Alright, so remember, 1 bond is made of 2 electrons, and those 2 electrons are being shared between those 2 atoms. Okay, now, so that's what it means. You either draw, you put 2 electrons, or you put the central atom, or you put the bond between the central atom and the surrounding atoms. Okay, so once you've done so, make sure you count the number of valence electrons. So I have put it in for 8 electrons total, because remember, 1 bond brings in 2 electrons, so that's a total of 8 electrons used in this case. And remember how many electrons we started out with in case of CCl4. If you go back, CCl4 has 32 valence electrons. So out of those 32, if I subtract, we have used 8, so we still have 24 more to go. And what I have said, we want to make sure we use all valence electrons no less than 32 and no more than 32. Okay, so we have 24 more electrons to go. So your next step is going to be use the leftover valence electrons to fill the octets of the surrounding atoms. Okay, so in this case, your surrounding atoms are the chlorines. So you want to make sure each chlorine has the octet completed. So when we say octet, means it must have 8 electrons when it has made the compound. Okay. Every single element that's acting as a surrounding atom will need 8 electrons when it makes a compound, except, alright, so make sure you memorize this exception, except the hydrogen. Hydrogen needs only 2 electrons, which technically means it's already happy when it has made one bond. All right. So hydrogen makes only one bond, and that brings in 2 electrons for this hydrogen, and it does not need anything else. Now, the reason why hydrogen needs only 2 electrons because the closest noble gas to the hydrogen is helium, and helium has only 2 electrons in there. Okay, so hydrogen needs only 2 electrons. Keep that in mind. Okay, so far what we know, each chlorine has 2 electrons. If I go back to this circles that we have made, each chlorine has 2 electrons in there. So that means to fulfill the octets of these chlorines, I would have to put it in 6 more electrons in there. Okay, so put it in 6 more electrons around each chlorine, and whenever you put in those electrons, you always put them in the form of pairs. Okay, don't put electrons all alone. You're always going to be doing them in the form of the pairs. Okay, so then recount your electrons. So when you put 6 electrons around each of those 4 chlorines, you actually use the remaining 24 electrons. So now you don't have any valence electrons left, or another way of saying, you have used all 32 valence electrons. Okay, well, there are going to be times when you have completed the octets of the surrounding atoms and you still have some electrons left. Now, in that case, all right, so that's rule 6. If you still have some electrons left after completing the octets of the surrounding atoms, those electrons go on the central atom as lone pairs, all right? So in this case, we don't have that scenario, but if that were to happen, those electrons will go on the central atom. So this is your Lewis-Strauss structure for CCl4. Okay, so keep in mind the bond that's made between the carbon and chlorines. Those are called bonding electrons, or they're also called bonding domains. So we want to make sure you know the terminology here. And then the electrons that solely belongs to one of the elements, like in this case, each chlorine has 3 lone pairs. Those are called lone pairs electrons, or also just called an electron pairs. The lone pairs is more commonly used term in that case. Okay, so this is how you're going to be doing the Lewis-Strauss structure. So let me take another example maybe. Let's say I'm trying to draw water. Okay, so the first thing I want to do is calculate the total valence electrons in there. So the total valence electrons in case of water, I got 2 hydrogen atoms, so it's going to be 2 times 1 because hydrogen atom has 1 valence electron, and then there are 6 valence electrons on the oxygen. So that's going to be a total of 8 valence electrons. Okay, so then the next thing is to pick the central atom, and in this case, what do you guys think? What's going to be the central atom? Well, remember the trick. Hydrogen is never a central atom, so that means oxygen is going to be your central atom in this case. Okay, so oxygen is the central atom. So then I will put the oxygen in the center, and then I'll put the hydrogens around it. Okay, and when you put the hydrogens around it, the very first thing you want to do, remember that rule 3, you place 2 electrons between the central atom and the surrounding atom, or another way of saying, place 1 bond between the central atom and the surrounding atom, just like this. And now you want to count how many electrons you have used. So 1 bond brings in 2 electrons, so that means you have used 4 electrons. So how much you have remaining? So your remaining electrons in this case would be 4 again. So you must use those remaining 4 electrons. Okay, so the next step is to complete the octets of the surrounding atoms. Okay, so in this case, the surrounding atom is the hydrogen. And what we have said about the hydrogen, hydrogen needs only 2 electrons, which usually comes when you draw a bond with the hydrogen and another element. Okay, so hydrogen is happy already as it is. You don't put anything extra, just 1 bond for the hydrogen. So if you can't put anything on the surrounding atoms, you still have these 4 electrons. What do? They go onto the central atom. Okay, So then that means I'm going to have to put those 4 electrons as lone pairs on the central atom in this case, so on the oxygen here. So you have 2 bonding domains. So remember, you got 2 bonds, so that's going to be counted as 2 bonding domains, and you got 2 lone pairs on the oxygen, so you're going to have 2 lone pairs. So so remember this terminology. We're going to use that again when we start talking about the Vesper theory and predicting the shape of the molecule. So this is how you draw the Lewis-Dot structure of the water, but we're going to learn in a separate video that water actually is a little bit bent. So for right now, just be able to draw the Lewis-Dot structures, and I'll have in a separate video where you determine how the shape comes around when you have different lone pairs and the bond pairs and all that. Okay. All right. Well, there are some exceptions to these octet rules when it comes to the central atom. So we already talked about the exception to the surroundings. Whenever you have hydrogen as a surrounding atom, it needs only 1 bond, and the rest of them will need 8. But in this case, if you have only 1 electron, if you have the boron, the compounds, and the beryllium compounds, they could have either less than 8 electrons or more than 8 electrons. What that really means, for the most part so far, we have been seeing the central atom should also have the 8 electrons, the octet completed, but there are going to be times when the octet is not completed. So it's called an incomplete octet. So the compounds of boron and beryllium are some of the examples. You can have a BH3, BF3, or BeCl2, or a matter of fact, any boron compounds. If I take an example of maybe BH3, let's count the total valence electrons. So the valence electrons in this case, boron has 3 valence electrons because it's in group 3A, and then each of the hydrogens will have 1, so that gives you a total of 6 valence electrons. Okay, so then what's going to be the central atom here? Well, hydrogen is never a central atom, so that means the boron has to be the central atom. So I'll put the boron in the center. And then I want to put hydrogens as far away from one another. So if you have only 3 things, you can put those on the vertices of the triangle as far away from one another, just like these. And then you want to place 1 bond between the central atom and the surrounding atom, or another way of saying you want to put 1 electron pair between the central atom and the surrounding atom. So if I put 1 bond between the central atom and the surrounding atom, then you want to make sure you count how many electrons you used. Since 1 bond brings in 2 electrons, so you have 3 bonds, so that's a total of 6 electrons. And that's what you really have to start out with. So you have actually used all the electrons. And now if you look at the octet, well, hydrogens are happy because remember, hydrogen needs only 1 bond and they're happy with it. How many electrons you have in the boron right now? The boron, since those electrons are being shared, boron's going to have 6 electrons in its octet. So that's when the octet is not completed, and it is still stable. For the most part, the compounds wants to have the atoms wants to have an 8 electrons, but there are times when they can get away with less than 8 electrons, and sometimes more than 8 electrons. Okay, so let's take an example of something that will have actually more than 8 electrons. Anytime you have an essential atom that's going to be coming from in either the period 3 or below, they could have more than 8 electrons in the octet, and that's called an expanded octet. So it's possibility. They don't necessarily have to have it all the time, but it's a possibility for them. Okay, so let me give you an example. Assume I have SF6. Okay, so anytime you have a compound that containing a nonmetal from a period 3 or below, so those could be phosphorus, sulfur, iodine, and so on. So in this case, SF6, count the total valence electrons. So sulfur has 6 valence electrons, and you have 6 fluorines, and each fluorine has 7 valence electrons. So that's going to be a total of 48 valence electrons. So do the math here. And then what's the central atom? Make sure you don't skip the steps. Your central atom in this case is going to be sulfur, because remember, whoever is the fewest in number is usually the central atom, or whoever is the least electronegative, which in this case sulfur is less electronegative than the fluorine. Okay, so then I would put the sulfur in the center, and then I have to put the fluorines all around, and just figure out the best way of putting the fluorines all around the sulfur. Okay. So then I want to put one bond between the central atom and the surrounding atom, which also means one electron pair between the central atom and the surrounding atom. So then you can see how many electrons we have used. So that makes up 6 bonds. So that means that's going to be 12 electrons used so far. And if I subtract it from 48, we still have 36 more electrons to go. Okay? The next step would be to complete the octets of the surrounding atoms, and in this case, each surrounding atom, the fluorine, has only 2 electrons so far, because one bond is going to be the 2 electrons, so that means each fluorine should have 6 additional electrons. So when you put in 6 additional electrons on each fluorine, so you're putting those in the form of the lone pairs. That actually uses up the remaining 36 electrons. So now, by this time, you have used all 48 electrons. Okay, so this is going to be the Lewis-Strauss structure. And if you look at the octets, the fluorines are happy. Each fluorines have 8 electrons at the end of the day. Now, look at the electrons of the sulfur. The sulfur is going to have how many electrons? It's got 1, 2, 3, 4, 5, 6 bonds around it, and remember, each bond brings in 2 electrons, so that means right now sulfur has 12 electrons on it, and that's completely okay. Sulfur can have more than 8 electrons in its octet when it's making the compound. It's not going to have it always, but it has the potential to have more than 8 electrons. Okay, so this is how you're going to be drawing the Lewis-Strauss structure. I'm going to have another video where you're going to be predicting the shape of these molecules. Obviously, this is not the best way of representing those in 3-dimensional in terms of the geometry, but this is how you're going to be drawing the Lewis-Strauss structures. All right.